I think we can get started. So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Nicola Bezzo, who is a professor with the Departments of Systems and Information Engineering and Electrical and Computer Engineering at the University of Virginia. So something about Nicola: he obtained his PhD in Electrical and Computer Engineering from the University of New Mexico. There he worked on multi-robot systems, motion planning, and control under communication uncertainties. And prior to that, he received his Bachelor of Science and Master of Science from Polytechnic of Milan. He also was for a while a postdoc at the University of Pennsylvania, where he worked on research related to assured and resilient autonomy. At the University of Virginia, he is the leader of the Autonomous Mobile Robots Lab, and he's also part of a founding member of the Link Lab, which is a new lab on cyber-physical systems. And his research in general is about safe and agile motion planning and control for autonomous robots in situations in which you have uncertainties, and also resilient and assured autonomy. As you have seen from his bio, he has won a number of awards, and he has had some very interesting collaborations also with industry. And today is going to talk about a new topic, which is, I'm going to read the title: I know that you know that I know, towards epistemic planning of heterogeneous robotic systems. This is something interesting for us in our lab, and that's why I'm very excited to hear more about it. And I give you the stage, Nicola. Go ahead.
Great, Joelle, thanks again for the introduction and for inviting me. I see actually among the audience, Ivan is one of the persons I collaborated, so I think he's going to be one of the next speakers, I think, in your, so I'm glad to see you, Ivan. But anyway, so let me get to start, okay? I would like first to give you a quick introduction. I mean, I'd like to give an introduction about where I am right now, also to motivate people also to come here and also visit. I'm going to minimize a second here, Zoom. So I'm at the University of Virginia. I've been here for about 6-7 years. I just became an associate professor. UVA is a really fantastic place to visit. It's a fantastic place to work. It's in the middle of Shenandoah Mountains, so it's a very nice place to visit, and there are a lot of wineries. It's a great place in general to work. There is a lot of activities. The school is big, it's complete, it has a lot of different area. It's about 25,000 students. So again, a great place to work. And again, it was founded by one of the founding fathers of US, that is Thomas Jefferson. About my laboratory, again, I was founded about around 2016 when I joined UVA. It's you can see a picture. It's not very updated, the picture, because we have more robots nowadays, but it's a state-of-the-art laboratory for mobile robots, simulation experiment. I have about 15 students between graduate and undergraduate, and I have about 80 mobile robots, so I deal more with legged UGV and UAVs robots. So with that, I have access to an outdoor facility. It's called Milton, and that I can run larger experiments. It's like a big airfield. And as Joelle mentioned, I'm one of the founding members of a Link Lab that was founded in 2016, and this Center for CPS Excellence is where I am right now. Okay, a little bit more details about my laboratory before we go into the details about the talk. So my laboratory is focused on resilience and agility and autonomy of mobile robotic systems. We are very applied. So we come from a motion planning control background with some machine learning nowadays, but we are very applied, and we have a broad range of vehicles that allows to test our capabilities. But we primarily focus on air and ground vehicle autonomy, and more lately we've been focusing more and more about this idea of heterogeneous systems. So when we have a multiple robotic system with different capabilities. Okay, so this is an overview about some of the projects that we have in our laboratory, and just want to give an overview about some of the things we've been doing. My work has been is funded by several organizations, from DARPA, NSF, ONR, to companies, industries, including Amazon, CoStar, that are large industries. But my research has been focused primarily on assured autonomy. And so how, for example, we can have a system that run machine learning tools and control level tool, data-driven, model-driven approaches, how we can have this tool that work together, and how we can make sure that this system can work and be safe and be able to guarantee that it can perform correctly. Because of that, we've been using a lot of reachability analysis, and so a lot of work on my team has been on runtime monitoring, on predicting, proactive monitoring, and the image that you see on the right kind of like describe it to be this idea how we can be proactive and predict forward what could happen, how we can have a system that can be again more attentive when it's making decision. We do some work on explainable and interpretable monitoring. As Joelle mentioned, we do work on resilience against cyber attacks. I have some projects related to the idea how we can protect and defend against cyber attacks on vehicles. I have also some project with Amazon related to planning a structured environment, but is the idea of dealing with occlusions. So how we can formalize occlusions, and you see an image here in the bottom. So it's this idea, how can we better plan, the motion of a vehicle when we know there is some occlusions and we know where somebody can pop up or maybe some obstacle around. So we have some formalism about that. And again, I'm not going to talk about this today, but I'm happy to jump into another talk if you're interested about that topic. So again, more things, human robot, mapping, co-design, sim2real, you name it, we do a lot of work related to mobile robots. What I'm going to be focusing today is really on work on multi-robot systems. And this slide here, again, can be overwhelming, but it's just want to show some of the work that we've been doing. And they're going to focus on a specific topic. But I want to show again how this idea came from and what we did in the past. And this slide, what they show really this idea again of using multi-robot systems, particularly the idea of heterogeneous robotic systems. So this is a prior work, some of our older work. But again, it's going to be used again to motivate some of the work that I'm going to present today. So what you see on the top is one of our earliest work of this idea of heterogeneous robotic system. This is probably like 10 or more years old. It was the idea that again to trigger this concept that 1 + 1 is more than 2. And here you see an aerial vehicle that is deploying this little crawler, and this crawler can go under a door to inspect a place. And the other vehicle can again fly this vehicle faster from one point to another one. What you see on the right is another thing. So, you see Spot with one of our aerial vehicles, and what's happening there is really the aerial vehicle supporting the ground vehicle, and I'm going to talk a little bit about that today. On the bottom, you see another operation that was an heterogeneous operation with in which we had that aerial and ground vehicle were coordinating different tasks. So it was more a task assignment problem, considering energy constraint. So that was the idea, how can we make sure that we don't run out of energy? On the bottom, you see some work we did on human-robot interactions. That is another form of heterogeneous system. And on the far bottom left, you see some of our work on heterogeneous systems, in which heterogeneous due to the fact that some of the robots are compromised. Again, this is just to give you an overview about some of our work that is very applied. But what I'm going to focus today is really about this idea of epistemic planning. Again, and that's what I'm going to start today, right now. So, with that in mind, so give you like a quick overview about my laboratory. Let me start with the talks by give you an idea about the motivation about the problem that I want to talk today. The motivation is simple. Okay, we have imagine you have an heterogeneous team of ground aerial vehicles that are tasked to explore an area. So you have some prior knowledge about the map of environment, but you may not know everything about the environment. If you want to explore an environment quite well, typically you want to split, you want to divide. And when you divide, what could happen is that you may lose communications. You may not have communication between the vehicles. And not only that, the environment may be different from what expected, maybe different obstacle, dynamic obstacle, and then you may find even tasks that require another vehicle. So what we would like to do, what our interest here is really to create policies considering these uncertainties, okay, and be able to create sort of like this cooperative behavior, even in the case in which there's no communications. So the idea is the phone, okay, we can disconnect, but we would like still to be able to maintain this cooperative behavior. So in other words, we would like to make sure that the aerial vehicle here, if we find a task that is appropriate for a ground vehicle, even though it's not talking to a ground vehicle, is able to find it easily and is able to route it appropriately to the task. Okay. Okay, so with these premises, our objective is really here is to design a strategy to enable a heterogeneous multi-robot system to achieve what we call like a robust and cognizant operation under these uncertainties in the environment and under limited communications. Excuse me. To solve this problem, we use epistemic planning that I'm going to go over more in details right now. This is a new concept that is developed by, it's not really developed completely by my team, but we are leveraging from another area and bringing to this into this area of mobile robot. So with epistemic planning, and we use some mixed integer programming to perform task and gossiping, okay, for the assignment. So let me tell you a little bit about epistemic planning, what it means and what it is. So I don't know if you ever watched the movie The Princess Bride. I'm not going to spoil it too much about the movie, but in this movie, that is, I have a snapshot on the right, there is a scene in which there is a criminal called Vizzini that is challenged by the hero, is called Pirate Roberts. And the challenge is that he's challenged by guessing which one of his glasses contain poison. So one of his glasses is poison, and the Vizzini, that is the villain, here the criminal, is challenged to figure out which one is poison. And all the scene develop around this concept in which the Vizzini is trying to outsmart the hero by using what he knows that the hero knows that he knows that the hero knows that he knows. So it's this idea of imagining ourselves in position of somebody else, okay? So he's trying to figure out what he knows and what he would, so he will have done based on what he knows that I know, that he knows that I know. Another example is what you see on the top left. Here you see that Bob, the guy here, knows the secret, and also Alice knows the secret. But Bob doesn't know that Alice knows the secret, and Alice knows that Bob doesn't know that Alice knows the secret. Again, this again is imagining ourselves in the position of somebody or someone else, okay? And this is under what is called theory of mind, okay? It's something that's been studied and has been again around for quite some time. But based on these premises, again, so that we can define what is epistemic planning. The epistemic planning is really using this idea again of putting ourselves in position of somebody else, or someone or somebody else. And this is an enriched automated planning that uses this epistemic notion that means include knowledge and beliefs. So that's the idea. I want to kind of like stop here for a second. It's the idea to include knowledge and belief in order to create a better coordinations. And what is great about epistemic planning is that we can use incomplete knowledge, because we may not know again how its environment, we can use incomplete knowledge and belief about this knowledge to better plan the motion of these systems. Okay, so this, what I just described, is actually very complex if you're dealing with humans, but the robots actually become a little bit more easy, because again, we can plan what a robot can do. That's the idea. Okay, so I hope this was a little bit clear with this example. So let me go back and show you again from this slide what we mean, what we can do with this idea. So let's look at this pictorial representation. Imagine like you have this UAV that find a task that is in which you need both a ground vehicle and an aerial vehicle. So what the UAV is doing here is trying to predict where this ground vehicle may be, okay? And based on this prediction, it's planning the best way to perform this task. So in this case, for example, the UAV may decide, okay, well, I believe that the blue vehicle is here. So I plan to go to talk to him so that he can go do a task, and then I go talk to the red one to tell him to go home because I found the task, and then the UAV go back to complete the task with the ground vehicle. The problem again, there can be problems, and as I can show you here, the aerial vehicle again goes to find the ground vehicle, it doesn't find it there. So what we would like to be able to broadcast more particles, we're gonna see that are more belief, but where we think the ground vehicle may be, so that we can find it and then route it appropriately. So in this case, for example, if the aerial vehicle doesn't find the ground vehicle where it was supposed to be, it may go to another belief, to a second belief. And then at that point, maybe it may discover that the ground vehicle is compromised. So at that point, it's going to have to change the missions, send it back to the base stations, then maybe then at the point, going to go to the other ground vehicle to tell him to do the mission with him. So again, this idea also to adapting based on what happened during the operations. Okay, if that is clear, again, I want to walk you now through the approach. And again, this is it can be a little bit a cluttered diagram, but there are three main components here. One is we have this frontier exploration method. We have this propagation of belief and empathy state that are used by epistemic planning to plan, again, the motion of a system when there is no communications. And then based on that, we do some task allocations. And this task allocation is used, again, to figure out where to send the robot. Okay, so let me tell you about the belief and empathy state that are the main concept for use for epistemic planning. So once the vehicle are disconnected, what we do, we propagate this belief and empathy state. So we define belief state, the predicted position of another robot. So if you look at the picture on the right, you see there is this UAV that is predicting where this ground vehicle may be, and is also broadcasting some other particles that are other state of possible other state of these ground vehicles. So you can think this, for example, could be other state, excuse me, of a vehicle if, for example, is compromised. For example, if he has a failure. For example, let me put here, this could be maybe a failure of 50%, this could be a failure of 20%. So where a vehicle is broadcasting all these particles that represent possible state of this ground vehicle. Together with that, we have empathy state, that are a predicted position of a robot from other robot perspective. So what it means, if you look at this picture on the right, on the bottom, where a vehicle is predicting what the other vehicle think about himself. So if predicting, okay, where do the other vehicle think I am? So at this stage, you may also wonder, okay, well, wait a second. So we have this discrete number of particles that represent possible state, but again, it's a discrete number of particles. There will be infinite possible things could happen to a robot, correct? So it's not necessarily that he has a failure of 50% or 20%. Well, that's not a problem in our case, because as long as the robot are able to match one of these particles, then we are able to guarantee that the system can meet. So what this means is that if this particle is 50%, this other particle is 20%, and the robot has a failure of 60%, then what happens, the blue robot is going to match its 50% particle, so that the other vehicle or other vehicle will be able to find it where it's supposed to be. Okay. So again, to summarize so far, what you're doing, so we are broadcasting these particles that represent belief and empathy state, and we use that as anchors whenever we need to meet, we need to find somebody else. Okay, so that's the main logic for epistemic planning, but together with that also we need to coordinate the system. For this work we use frontiers-based navigations. And you should be familiar, I think you may be familiar with Frontier, but Frontier again allows us to again consider these boundaries that are in Explore, and we use occupancy grid mapping and to figure out what are the areas that are in the perimeter that are between known and unknown space. And then what we use some cost functions, so we use some utility function to be able to figure out which of these frontier to assign to each robot. How we do that again is considering what are these belief and empathy state and this common belief, okay, for all the particles for this robot, and we define the common belief as the state where the robot was last seen, and we propagate in that state. So what I mean with that is that if after we disconnect we never saw each other anymore, we consider actually for example, these that is here, the more likely particle, the more likely state of the robot. Anyway, with that in mind, again, what we do then, we assume we have again some sensor field of view of each robot, and we compute the frontier for each of these particles. And then we use some similar to a Voronoi partition in order to assign what are the frontier for each robot. So you can think that each of these square that you see in this image are again a possible frontier, and you see a different color represent what are the frontier assigned to each robot. And again, it can be assigned just by splitting, based on distance. But what is interesting, what you're going to see in the next slide, is that we can also shift and weight differently based on the capabilities of a robot. So if a robot is going slower, you're going to assign less of this frontier. If it's going faster, you may have actually more frontier that you can assign. Okay, so with these two things already in mind, we can already do something very cool. And I'm going to show again a first implementation that was presented actually at ICRA of this idea of epistemic planning when we have failure in a coverage problem. So what you're going to see in the video on the left, you're going to see two robots that they have the same capabilities in this case, and they split and they try to cover an area. Okay, so what you're going to see here again, we're going to start to split, and again, as they split, they broadcast these particles that represent possible belief. And as you can see here, again, orange has a failure at some point. And so what happened now is a failure of 30% here. So what happened is going to start to track its second best particle. But what you can see, blue is tracking the one that is more likely. At some point in this mission, you're going to see that the robot wants to meet. You're going to see, they're going to meet. And again, blue, it doesn't know about the failure this stage. So it's still broadcasting again all particle, and it thinks the orange is going to be here. So as this advance, you see at some point it wants to meet. Okay, because that's how it was defined the problem. We had that they want to split, but at some point, there is something that costs that allows them to meet again. What happened here, again, that's the interesting part about the epistemic plan, is that blue, of course, knows that it doesn't see orange here, because it was supposed to see it, it doesn't see it. But orange also knows about that. Orange here knows that blue is trying to meet with orange, and he knows that it doesn't see it. So again, we have some, because of that, again, we have some common knowledge here, okay? So we have some common knowledge that allows them to figure out, okay, they both know that they're not there. So at that point in time, they switch into a different mode, and they start to have a second particle now that tend toward each other. So they track the second particle so that they can meet with each other. So what you can see here, again, the second particle try now to meet. So both robots try to track this line so that they can meet. Okay. So again, they are able to achieve a consensus even though they're not talking to each other, based on what they're supposed to, where they're supposed to be, and based on what they predict to each other. So after they meet, again, they reshuffle the missions. The blue now knows the orange cannot perform as well as before. So there are more frontiers assigned to blue than to orange. And in this way, we are able to, again, optimize the missions. We're able to complete the task. In this case, was just a coverage task. The other video that you see is a similar story, just with different type of failures. You see, for example, we have a 60% failure, but again, the robots are able to meet thanks to our epistemic logic, and they're able to complete the task as efficiently as they can, because again, in this case, orange cannot perform as good as blue. In the last simulation, you see another similar scenario, but in this case, you have 2 failures. But again, thanks to our epistemic planning approach, they can predict where to meet, how to meet, and how to, again, shuffle the mission so that they can cover the environment. Okay, so that again is an example of our epistemic planning. And if this is clear, okay, and again, if you have questions, please don't hesitate to ask. But if it's clear, again, based on that, then what we did was we moved toward a heterogeneous system. Before doing that, I want to show actually a comparison. This slide shows comparison between the 3 methods. In the middle is our proposed method. On top, you have if you are always connected, if you always need to drive together in order to maintain connectivity. In the bottom is ideal, meaning that if you have infinite communications. What is interesting here is that you see that over, if a number of failures grow, okay, what we see is that our approach tend to get really close to the ideal one. So even though we are not able, again, to have these infinite communications, thanks to our epistemic planning, we are able, again, to perform the task, again, getting closer to an ideal case in which you have always communication enabled. Okay, so that's again our premises for epistemic planning. Again, as I mentioned, what we did after that, we move a little bit on, we move our implementation a little bit harder to have a little bit more constraint, and we add this idea of heterogeneous systems. So heterogeneous system for us in this application is a robot with different capabilities. In this case, we have aerial vehicle that can move faster and ground vehicle get a little bit slower. So what happened here, I'm going to drive you through these pictures. We can have aerial vehicle that is faster, it discover a task. We can still have failures. So we have these particles that are propagated about each robot. Once we discover a task, then we need to be able to assign where a vehicle here found that this task need a ground vehicle. So for example, here, if think that the ground vehicle is here, so he route, himself toward that robot, he may discover that it's not there. So locally, we need to update what we believe about the robot, and we need to update also the missions. For example, in this case, if initially we want to have a green going to the task, we may decide now that actually green is so compromised that it's better to send to the base station, and it's better actually to go to talk to red to do the task. Okay. So again, there is a few things going on here. There is a epistemic planning to predict where everybody is, and then there is some task assignment to be able to figure out where to send everybody. Okay, so now I'm gonna quickly go over the task assignment. As you know, again, task allocation is a complicated problems, and so in order to solve in our case, we use some mixed integer programming. It's a mixed integer nonlinear programs, which we try to maximize some utility for each robot assignment, subject to a fact that we need to have all tasks need to be completed by a necessary number and type of robots. We have some precedence constraint, as always, for task ordering. And then, of course, we need to have a constraint that tasks are completed after a mission start, and we have some assignment that are binary. So again, this is a very complicated problem to solve. So in order to solve that, as you already see from this slide, we use some genetic algorithms. So we start with from this constraint algorithm, this constraint optimization, we transform into an unconstrained optimizations, and we penalties. So we give penalties if any of these constraints are violated. In order to solve that, we represent a solution space. So the solution space you can think as whenever we find a task, we consider what are all robots available, okay? And we consider all possible epochs where this task can be solved by any of these robots. You can think epoch like, okay, I need to open the door in order to have a robot entering the door. Okay, so these are different epoch. But long story short, again, in order to solve that, we use some genetic algorithms. We start with initial solutions, and then what is good about genetic algorithms is that it can quickly sample the solution space to find the solutions, and they try to find, of course, the best solution possible. And we have actually, in our case, we're able to demonstrate actually that overall, again, it's working quite well. We get pretty much the optimal most of the time. We cannot, of course, guarantee, because again, it's an heuristic, but again, it works quite well, and it's quite fast, actually, in our case. So the solution that we provide is a set of goals, and it could be two types of goals. It could be a gossiping assignment to route a robot to a belief state, or a task assignment to route a robot to a task location. That are the two things that we found. Anyway, so long story short, if you put together this task that is again computed also at runtime, that's what we obtain. So in this mission, you're going to see we have an aerial vehicles that found a task, and he knows here in this mission, we know there is only one task, but we know how many robots are needed, what is the task. And so the vehicle found a task here because it's faster, and he figure out that he needs a ground vehicle, and he's going to see he's going to change the assignment because he found out that green is compromised. So let me start the video. So again, the aerial vehicle is a flying, and there are these beliefs that are propagated. He thinks he found the green here, but he doesn't. He go to the second. He found that green is compromised, so he send it home. He go to red, so that red can go into the task. And once the task is completed, they go back home. So again, basically, this is the epistemic planning to propagate these particles and to figure out where to go. If something changed, then get reshuffled, adapted at runtime, so that the mission can be done as optimally as possible. So that was a case with one task. Here you see some case in which we don't know the number of tasks, so we have some coverage problem here. And you see the comparison between flocking, our proposed method. So flocking here is assuming that they need to be close so that they can talk all the time. And this, of course, is not optimal. And the two videos here on the right are the proposed versus ideal. Ideal means that, again, as before, we can talk everywhere. We have infinite communication. But what is interesting, again, that you see that our proposed epistemic planning with this task assignment, it gets closer to the ideal case. And again, ideal case is not something that is possible. Okay, so again, some result. So again, these are some results in which we have a random number of obstacles, randomly generated failures, and we have a number of robots. I think we will test until 8. We actually did 10 and more, but here we're saying a result for 8 robots. These are results for about, I think, if I remember right, 50 simulation for each case. And as you can see, again, you see that as a number of robots increases, again, given these failures and randomness in the environment, you see that our approach tend to be closer to the ideal one. So again, so that demonstrates that even though we are not able to communicate, we're able again to create something that is very close to an ideal case in which communication is infinite. Okay, so hope is more or less clear. And in case again we can have more questions, we'll teach you some experiment. These are in lab experiment. So this is a case in which you have one task similar to the simulations. And again, here, the robot, you can see they're exploring based on this frontier method. The other vehicle, you found the task. And then if you go out that the blue vehicle was compromised, so you send it to the stations, go to the red one, and then they all go back home once the mission is done. Next is another operations. In this case, we have unknown number of tasks, so become a coverage problems also. And cover is because, again, because we don't know the number of tasks, we need to cover the entire map. So again, as the vehicle found tasks, they all figure out where to go, where to meet, thanks to epistemic planning. And once the tasks are done, again, they all converge to a common place before going back to the base stations. And yeah, so that again is to show again some demonstration with real hardware. And again, these were all run again, all runtime. So again, everything was computed at runtime as the operation you see it happening. Okay, so with that again, I hope I demonstrated and I motivated a little bit this idea again of epistemic planning. But again, by using this idea of belief and empathy, we can create this consensus, because again, everybody is thinking what the other is thinking. And because of that, again, they can figure out a place where to meet. They can find a rendezvous. They can always find a way to meet and perform an operation, even without communication. Great. With that, I want to show you now some recent work we've been doing expanding this idea. And we're expanding this, by the way, in different ways. I'm going to talk in 1 second. But one thing we've been discussing with my team is this idea of really augmenting actual system capabilities. So you saw some work on a heterogeneous system, which a vehicle go find a task and then go back and is seek help from another vehicle. But one thing we realize also that often we have this vehicle have limited capabilities and they can be into dangerous situations. So what we start to think is that why can't we just leverage this idea of again epistemic planning and build a sort of like a system of systems. So we're trying again to formalize the idea of system of systems, in which you have that again aerial vehicle, in this case is assisting a ground vehicle. So we still have a heterogeneous system, but you can think, for example, in this case that the ground vehicle maybe cannot see hole in the ground, let's say, oops, cannot see hole in the ground, and before we can send a vehicle, it can figure out there is a problem, then send it back and reroute the ground vehicle so that it can go around and find the best route for the ground vehicle so that it's safe. Not only that it's safe, but also it's probably a little bit more optimal. Okay, in order to solve that, again, I'm not going to go too much in the details, but to use again some epistemic planning in order to rendezvous with the ground vehicle. So the vehicle is assisting the ground vehicle. Use some frontier again method again for explorations, and then use some self-event trigger planning in order to figure out when to go back to the ground vehicle, and some other predictive path integral in order to optimize waypoints for the ground vehicle. So in other words, we are not sending the entire route to the ground vehicle. Whenever a vehicle found a new path for the ground vehicle, it will just assign some waypoint. So here you see a pictorial representation on the right. You see, for example, here, because of a cul-de-sac, the ground vehicle may get trapped in here if it's not, again, if you didn't know about that. But if every vehicle is able to scout the environment ahead, it may find actually an alternative route so that the vehicle doesn't waste time to go through that place. So the video you see on the bottom is an illustration of that, and it's running all of these different concepts. So the environment is partially known, and you see the vehicle is broadcasting particles where the ground vehicle may be, and then it found again an alternative path, and based on that again is able to reroute the ground vehicle to the optimal path. The next video I want to show you just about the model predictive path integral aspect of this work. So here red is a rough terrain. You can think like mud or sand. Okay, so again, the vehicle figure out that and is trying to look for an alternative path. Okay, so it's looking for an alternative route for a ground vehicle. At some point again, he found a better path. You're gonna see, and you see like he's monitoring where the ground vehicle may be by the time he's come back. Whenever again he come back, as he's coming back, actually is optimizing the route, and they are just illustrating by showing what's happening. But what the model predictive path integral approach does, really computing several alternatives, is actually sampling different waypoints, and then is scoring different waypoints, and then based on that, is putting everything together to figure out what are the best waypoint to send the ground vehicle, so that is able to avoid this area that again is mud in this case, so it's not dangerous, but it may actually slow down a little bit the ground vehicle. I want to show you again another video, again, because again, video typically are more easy to visualize. This again show our complete approach. Again, we're working in an accurate paper related to that. And you see again here we have black that are obstacles that were not known. Blue actually you can think as a pond of water, so holes which a ground vehicle may fall. And again, pink is mud, so things that are not really dangerous, but it may slow down the vehicle. So this here again, the vehicle again is doing most of the heavy lifting here. So it's scouting, he figure out again problems in the area, he go back to area where again, he come back to the ground vehicle and he find the solutions, he optimize the route so that the ground vehicle can go around, be safe as it's navigating for this environment. So again, this is not only for safety, but also to optimize the entire operations. And what is interesting, as you can see, is that although the aerial vehicle find that there is a better path, you see here, for the ground vehicle, it doesn't feel is necessary, or if the cost is such that it's not worth it to go talk to a ground vehicle. So we let it go for like a mud here, because again, it was not such a cost so negative that it's going to impact too much the vehicle. Again, so that again is just to show again another type of application of leveraging this epistemic logic with a little bit more on now looking to the system or system aspect of these heterogeneous systems. Here I show an experiment in the lab. This was some preliminary result. Here we have again a ground vehicle is trying to go to this goal, and there is some objects that are obstructing the emissions. And you see again where the vehicle is navigating, scouting the environment, figure out that the ground vehicle will not be able to get through there. So it come back before he make a turn. Then it decides so to go for the other path because of that. And again, where vehicle is still scouting ahead to do that. But again, by doing that, again, we optimize, we try to optimize at least the ground vehicle path so that it doesn't get stuck in minima, or it waste energy for because maybe it was going to go inside this cul-de-sac. Okay, so that again is a demonstration of this approach, and we're doing again more and more tests right now in preparation for the conference. Now, okay, so with that again, I pretty much I want to conclude here my presentations. I would like to mention that. So what I present today again is it's a novel approach of thinking about motion planning, which would bring this idea of belief and knowledge and empathy also. Right? So this allows again to navigate the vehicle when there is no communications, because everybody is predicting what everybody else thinks about the other robot. Again, I present also quickly, briefly, a mixed integer program for assigning tasks and gossiping information. That's something we are constantly working and iterating. As you know, it's a challenge problem, but again, we're doing more and more on that topic. One thing we are doing right now, we are adding more constraint into our approach, and specifically we're adding even more complex obstacle. Maybe things you may wonder, okay, what happens if we have really large obstacles that are unknown? How can we make sure that you're able to broadcast correctly these particles? So we have some ideas about that, and we're using some. We are using again some approaches that allows again. We're using actually some partial observable Markov decision process to be able to figure out where the vehicle may be, and so more on that will come soon. And what we're doing more outdoor implementation. So you see like some of our settings. We have again some with our ground vehicles and one of our aerial vehicles. Again, they're definitely heterogeneous in the way they move and way they sensor. And we use again cameras to recognize object, environmental aspects. So we have some machine learning going on to help with these operations. Again, with that, of course, I have to mention I pretty much I did little about that with a presentation with the work of my team. Lauren, Shija, and Patrick are the architect of this technique. Here I have some QR code, but again, these papers are already available. So ICRAM, Frontiers, and IROS. IROS will be present again in a month or so, in October. So I encourage you to go if you're going to IROS to go and attend Lauren's presentation on that. But again, we have also other works again at IROS that are related or similar, or something that's very interesting. So definitely encourage you to go and see what my team is doing. With that, again, I would like to thank you and leave it open to questions, leaving with this image of one of my robots scanning the link lab where I'm sitting, and this is my office, by the way. All right. Well, thank you for the opportunity to present this work.
Thank you, Nicola, for the great talk. Let's open the stage for questions. You can either unmute yourself and ask, or you can also type in the chat and I will read the question for you. So who wants to go first?
Hi, yeah, can I go first? Thanks, Nico.
Oh yeah, go ahead, Ivan, go ahead.
Yeah, thanks. So maybe I missed it, but I wanted to ask more specifically, what's the role of the epistemic logic in your approach? Is it just the source of constraints and specifications on what the robots know?
So epistemology again is for us is to be able to find each other's whenever we don't have communications. So the idea is really about, let me go back, see if I can. So the idea of, talking about going back to, let me try to find the slide that can illustrate that. So that's the idea. Okay, so again, the epistemic logic, what it's doing really is broadcasting. We're broadcasting this belief state and empathy state, and in this way, we are able to find each other's. So the idea is that if there's an aerial vehicle need to talk to this ground vehicle, okay, but there is no communications, okay, and you need to again be able to figure out where it is, okay. So and there can be problems. There can be disturbance and failure. So if this robot gets stuck somewhere, okay, the robot need to be able to find it. So thanks to this belief propagation, we are propagating this belief state, this empathy state. Everybody is able to figure out if everybody is okay at every stage. So
okay, yeah, no, I understand that. I was asking just the logical aspect, like, are you making some statements in that logic or propagating the statements in it?
From the implementation point of view, you're asking how is that implemented?
Well, more from the, like, if it's a logic, you can make assertions in it. You know, the UAV knows where the UGV is or doesn't know. And so
Yeah.
Are these statements changing over time, or are they fixed?
No, they're changing. Of course, it's changing also based on when you meet with somebody, and then based on that, they get updated. But what's happening is that, okay, so what's happening is that the aerial vehicle, each vehicle is predicting where everybody is moving, okay, because we have a common planner logic, okay. So everybody is thinking what the other are doing, and based on that, is making a decision, okay.
I see.
So
I see. Okay.
blue is predicting, okay, is here, and red is here. Based on that, is they decide, okay, where is the red going next, where is green is going next, where I'm gonna go next, okay. And based on that is also putting the shoes of everybody else. Is thinking, okay, what happened if blue is what happened if red is compromised? It has like 50% loss of power or 20% loss of power. Where it will be, okay. And so so that's what they're keeping is a logic, okay? And the logic is saying, okay, well, if it's perfect, red is gonna be here. If it's 50%, it's gonna be here. If it's 20%, it's gonna be in this state, okay? Now, let's say that blue needs to talk to red and it doesn't find it here. Now, red also knows about that. Okay, if the purpose of this was actually to meet at some point, both they know about that. So based on that, then so they all figure out how to meet because they know what each other is doing. If you're not were supposed to meet, okay, then still you want to have that red is able to track one of his particles so that blue is able to find it.
Okay, understood.
But
Thank
yeah,
you.
we're keeping this logic. Yeah, so every single robot is broadcasting these particles that represent a possible state. Okay, and that again is where we think this robot may be. And of course, there is a distribution. So there is of course there is some priority. So for example, in our case, we have this priority 1, 2, and 3. Meaning that if I don't find on the first particle, I'm going to go to look into the second and to the third one.
Cool. Thank you.
Yeah, I guess one thing I want to add that is connected to what you're saying, that you may wonder is that, well, but we need to be able to reach these particles. So one thing we have as our assumptions that is needed is that each robot is moving with some nominal velocities. So it means that they're not ever pushing to the maximum, because otherwise we may chase somebody to forever and never be able to meet it. So that definitely is something necessary, because otherwise you're not going to be able to meet everybody.
Thank you for the question. There is another question in the chat from Mickey Lee who says, thanks you for the talk. And also they ask, what is the computational complexity of all of this prediction and how does it scale?
Yeah, so I don't know the exact number. So it's, I need to ask my student about that. I know that for for the task assignment, for task allocation is big O M N square, I think, where N is a number of robot and M is a number of tasks. So definitely it grows with the number of tasks and number of robots. But again, in terms of, again, of realization of this approach, we were able to again run up to 10 robots, and we had, for each robot we were running with 3 particles, and we had, I mean, like random number of tasks, and everything was running very, very quickly. In order to answer a little more about that, I mean, again, you probably had to check in the paper of my student, and I'm happy also to put in touch with my student for that. But one thing we are thinking about improve the computation complexity is to divide the team into sub-teams. Since again, we're able to run for, again, 7, 8, again, robot quickly enough. We're thinking about, okay, so if you have a team with 100 robots, why don't we divide these like in sub-teams? So if each sub-team is, is just dealing with, other 8 robots. So in that way, we can keep the computation lower. But again, going back again to the task allocation, that is of the, but the thing is, the things that was getting a little more requiring a little more computation, I think was big O M N square. So N is a number of robot and M is a number of tasks. If I remember, that was the computation that was needed. For the epistemic logic, again, it's of course it grows with a number of robots, but the point that each robot needs again to just predict. So it just depends on the number of robots and number of particles. So it's N times the number of particles for the epistemic logic.
Okay.
So
there are, Mickey, I think the question was answered. There are a couple of other questions. So I'll just go in order. Jonathan asks, what kind of models do you use to update the belief states? And maybe I'll add a twist on that, which is something I also was wondering. You mentioned nested beliefs at some point, or at least that's what came to mind. At which level do you stop? You could go on and ask the question forever. So,
it can become quickly complicated. Yes, definitely. So first of all, about the model, again, we use some holonomic skid steering model for the vehicle. For a UAV, I think we use some minimum jerk type of model. So it's like a jerk third order model for the aerial vehicle. And that, again, that is used just to model again the vehicle how they're moving. Okay, and you were asking about this nested belief. So that, again, you need to have some anchor to answer that a little bit in a simple way. You need to have some anchor for each one to be able to figure out where they are. What I mean with that is that if one vehicle found a task and the other vehicle is trying to find for that robot, okay, it may never find it. Imagine like blue. Okay, let me use this example here, but I have slide. Let's say blue find a task, and right now need blue. Blue, because it's going to a task, he find a task, so he go to a task, he may never find, okay, into the first particle, second or third particle. So the way that we solve that for now is assuming that we have enough robot to be able to perform any task. What it means with that is that if I'm not able to find a robot and I visit all these particles, I don't find it, I just give up with that robot and I switch and try to go and look for another robot. Okay, that's what we do. But yeah, I think you're moving the right way with your mind, because it's a tricky, and that becomes even more tricky whenever you have a larger obstacle. If you have a larger obstacle, the robot may, of course, try to avoid it, and you may propagate particles that drive through these obstacles. So you may never find that robot. And that's the reason we're moving to this. We also try to include like a more realistic obstacle scenario, because again, we are assuming we can, whenever we see an obstacle, we can understand what type of obstacle is, or have like some distribution about the obstacle. And based on that, then we can assume that, I see this larger boulder, and the boulder typically is big. So if I know that I was supposed to meet in 5 minutes a robot, and it's coming from the other side, I may know that I'm never going to meet him because of the size of the boulder is going somewhere else. So we are using all of that again now. We're using some more probabilistic method to be able to figure out where this particle may be. I hope it answered the question.
Yes,
the principle,
absolutely.
we're trying to use it to have some common anchor. Okay, so the idea is that we need to make sure that I need to make sure to be able to track a particle, and everybody else is able to predict that particle. And for simple obstacle, we can deal with that because you're just simply deviating and you go back to track your particles. If you have larger, it can become a little more complex.
Yeah. Another follow-up question I have on this, thank you for the answer. Another follow-up question I have on this is, you showed examples where the cost function for which the actions of the robots were evaluated makes the robots collaborative in some sense. But have you thought of applying this to competitive settings? Let's say robots that have to race, or that have to, even in the coverage example, they have to cover more area than the other in a set time, for instance.
Yeah. So in a certain sense, there is that aspect for the coverage, again, because we're trying to, again, the point of the coverage here is trying, especially for the heterogeneous part, with the show of the heterogeneous robot, we are trying to make sure we cover the largest possible area as far as possible from anybody else. For the example that I showed about the failure with the homogeneous robot, we actually were meeting at some point, so that we were trying to push away, but at some point, because of time, we were trying to reconverge. So we haven't looked exactly at applications, like to have, for example, racing, but I honestly think that could be reasonable, just a matter to change you're dealing with the cost. But that I think would be interesting because you could propagate where you believe everybody else it is. So if you're trying to avoid it, you're gonna, again, you're trying to push so constantly away from every particles.
Exactly.
If you're trying to capture, you may try to find actually a better strategy to capture it. But yeah, we're looking more to the collaborative aspect. Yeah, definitely.
But it makes sense. But I've seen, it reminds me of some, for instance, also a big application now in robotics is intersection handling, or merging of vehicles. I guess all of those could be cool applications of this concept.
Yeah. The risk, the only risk you can have of that, just thinking loud, is that because of this particle, again, the more particle you have, the better is the representation of your system, what could happen. You may find a certain case in which, there is not a feasible solutions because you're trying to be safe. So you're never gonna maybe overtake somebody, or never, you're always gonna slow down. So one thing we're doing, but in another area, but it could be connected to that, is going to evaluate some sort of like risk, meaning like likelihood and consequences. So if you know that the likelihood something happening in one of these particles very small, then you may be more willing to take some risk and overtake somebody in that case. But yeah, that's a good idea. I think, this definitely can be used to broadcast particles that represent possible things could happen with different likelihood, and then you can take, a risk associated with that. Yeah.
Thank you. Very interesting. There is also another question from Mickey Lee, who asks, another question I have is that in your scheme, the belief or empathy states are primarily locations. Could this approach be applied to different scenarios with different states, for instance, discrete actions?
So the initial work, if you look at initial work on epistemic planning, was actually, we didn't invent the epistemic planning word. We just take it and model and change it, adapt it for motion planning on mobile robot. The initial work was actually applied for humanoid robots, and we're trying to understand what humans think and empathize with the human. So there is some example in which, there is a human that go out of a door, and then something change inside the room, and the robot is trying to help and guide the human because he's trying to figure, okay, he went outside, so he doesn't know that these things happen. So it definitely it can be used for any other type of state notions, as long as there is some belief about something and there is some actions connected to that. I think this could be applied to other domain. We haven't thought too much about that because we work on this area, but again, it's all a matter of beliefs and empathy state. So you can believe anything, happiness, sad, person is sad, or you believe something. Maybe you can change how you operate. You can think also other type of state, honestly. So.
Great, thank you. So there is, I think, a final question from Pengji. Thank you, Professor Bezzo, for the great talk. I have two questions about the experiments. The first one is, it seems that the environments in the simulation are mostly in a discrete grid world. Are there experiments also in continuous settings? Would this setting make the scenarios much more difficult? I think in some sense you answered.
Yeah, the robots are moving in continuous fashions. We discretize just the occupancy grid map. So we have a occupancy grid map to be able to sample the frontier and figure out where to go next. So the ground vehicle actually have sensor, of course they have LiDAR, and based on this we discretize the environment. So we just create voxel, and each voxel now, if it LiDAR, you get, it's similar to any occupancy grid mapping. We get again, we get a probability if it's occupied or not. So we discretize the space in terms of for the occupancy grid and for these, what you see here, what you see also in this slide for the frontier base. But the robots are moving in continuous fashion, going from one point to another one. So the frontier, our goal, and as the robot moves, we get updated. So you can think be as simple as a PID that is trying to track a point, or can be more complicated like an MPC. I think some of our work use MPC to track, some other use potential field. Again, you can use whatever you like there. But yeah, we discretize the space, but the robots are in continuous. And just want to mention, the experiment in the lab, of course, the aerial vehicle is a tiny one, didn't have a LiDAR. So we were simulating the LiDAR on the aerial vehicles, but it was a runtime simulating. So as the aerial vehicle was moving, because we have icon motion capture system, it was in a certain position, we were broadcasting a circle underneath the vehicle to show that it was detecting that certain obstacles. Outdoor, we can use cameras and other things. It's actually simpler outdoor from that point of view because we have larger vehicles. I hope it answered. If it doesn't, please let me know. I don't know if I misunderstood the question.
Yeah, it seems so. When she said, got it, thank you. And with that, I think if there are other questions, you can reach out to Nicola. I guess you had your email somewhere, or I had it in the description of the talk.
And my student, again, I'm supposed to, you guys should have a recording, but please reach out to my student. Everyone definitely know more than me about this. One other thing I wanted to mention also that if you're interested about this topic, if you're in the market, I have to say that, I'm starting actually soon more projects related to this area. So I'm looking for both PhD and postdoc students to work in this area. As you saw, we have a lot of equipment, a lot of opportunities. So please reach out to me again. I'm actively looking for students that are interested about working in this area. Again, there is a lot to do. I think it's an exciting area. I really like this area. So please, again, don't hesitate to let me know. I would be happy to talk to you or more. Okay?
Thank you very much, Nicola. That's great work, and good luck for the next steps.
Thank you.
I will reach out to you when I edited the video, but it's been great to hear more about your work.
Yeah, thank you. Thank you for joining, and I'll see you at Tyros.
Yes, absolutely. And thank you all for participating. See you all next week for the next Autonomy Talk.
Okay, thank you. Take care.
Bye-bye. Thank you.